Can I start now? Please give me the okay to start, because I'm not sure if you can hear me fine. Oh no. I wonder why I can't hear you. Maybe it's better if I share the whole screen. Yeah, I don't hear anything from the room too, but sorry. Mm. So the host tells me that I shouldn't start. Yeah, that's okay. I just don't have the go that I can start. I'm sorry. Okay, awesome. Thank you so much. I don't hear if anyone introduced me. My name is Lisa Schielicke. I'm talking about a blocking identification method, and you already should have seen the video on the screen. We can see, or my talk is about atmospheric vortices and a specific type of pattern that stays put in the same region for a certain time. A nice way to identify vortices in the atmosphere is a water vapor image like the one you see or the video you see online, where dark patches represent dry air and lighter colors represent the moister air, and white patches even deep convection. This video was for about 6 days, covering the European continent, and we can see two low-pressure systems, one over the Iberian Peninsula, a high-pressure system over the North Atlantic region, including France, Great Britain, Scandinavia, and another low pressure here over Italy and southeastern Europe. This system stayed there for several days, and it caused several record-breaking events. For example, in the high-pressure area, we observed record temperatures in France, widespread flooding over the Iberian, or in Spain over the Iberian Peninsula, flooding also on the southeastern part of Europe, and finally this low-pressure system a few days later moved southwards towards Libya, and due to this heavy rainfall, the dam broke, which caused around 11,000 fatalities. Atmospheric blocking, or the system, the weather pattern behind these extreme events, is called atmospheric blocking, and this usually lasts for several days in the same region, and it blocks the typical westerly flow of the mid-latitudes. We have seen that this can cause extreme weather like heavy precipitation, flooding, heat waves, cold spells, thunderstorms, or snowstorms. Also in Canada, we have atmospheric blocking systems which can cause really extreme temperatures. For example, or in this case, we have a heat wave or record heat occurring in the Northwestern Territories, far beyond the 60-degree northern latitude, with about 35 degrees here on this yellow point. And the reason, if you look at the 500 hectopascal geopotential height pattern, is again a blocking system with one high pressure system towards the pole and two low pressure systems located equatorwards. Atmospheric blocking can have different types. The two examples I showed have been omega blocks consistent of 3 vortices. And there's also another pattern called high over low, or Rex block, which is one high located towards the polar side and one low towards the equator side. As well, there are extended ridges, but I won't talk about these today. There is a multitude of identification methods for blocking. It goes back to Rex identification or definition of a blocking in the 1950s. And Barrio Pedro and his colleagues did an overview over different methods, divided into absolute field and departure fields, and subjective and objective methods. And nowadays, there are also machine learning approaches which can be associated with weather types, for example, also with anomalies. However, what's still missing is an automated dynamical open source classification method that can be used to differentiate between an omega block and a high over low block. And this is what I will talk about today. So we have our data, wind fields, and geopotential height fields at 500 hectopascal. We first identify the blocking region, so where it is blocked. Then we calculate blocking properties, or the associated vortices, the properties of these vortices. And then we decide what type of block it is, and then we can do statistics and stuff. So I will talk more about the method today. The first step is identifying the blocking longitudes or latitudes. I just used in my method a very simple one, the Tibaldi and Molteni blocking identification method, which evaluates at a central latitude. This can be just a constant value or some climatological value of a latitude where the storm track usually occurs. And then it investigates the gradient of the geopotential height towards the northern and the southern side. And if we have reverse flow, we say that this particular longitude is blocked. And then blocking is large-scale patterns. So we assume that there are at least 15 blocked longitudes, and then that the block lasts relatively long, so for at least 5 days, which gives us a pattern of longitudes a long time, so a Hofmöller diagram of blocks. And these yellow regions here are blocking regions, and this helps us to determine the location of the blocking height. In the next step, we use kinematic methods and point vortex theory to investigate the block. And first, we have to identify the vortices. So what I plotted here is the geopotential height pattern in black. contours, and the colors are the vertical vorticity, relative vertical vorticity, with blue negative or anticyclonic and yellow cyclonic ones. I use the kinematic method, which is also relatively old, from Truesdale, proposed in 1953, and it evaluates at every grid point in the field the magnitude of the rotation and the magnitude of the strain. And if the rotation is larger than the strain, then we say it's a vortex. If it is exactly one, kinematics shows us that this is an exactly pure shear, and if it's smaller one, deformation prevails, and I say it's not a vortex. So first I identify every line here in red and blue where we have a kinematic or a WK number of 1. So these are the edges of the vortices, and then I cut out just the vortices and extract the vortex from the field. So everything which is white is thrown away, and everything which has a color is a vortex area. This is necessary because I want to use or go back to theory and use point vortex theory to investigate the vortex system. Here in this case, it's an omega block formed by 3 vortices, and a point vortex is now just our, we contract our vorticity in the whole area to a point so that the circulation stays constant. And each vortex then just lies on a point with a constant circulation. Each point vortex induces a circular wind field around itself, and all the vortices move within the field. So now we just have our 3-point vortices, and these move as a vortex example under certain conditions towards the west. And these conditions are that the total circulation of this 3-point vortex system is 0, and the vortices are located approximately at an exactly at an equilateral triangle, but you see in reality it's not an exact equilateral triangle. And then this system is counteracting our typical westerly flow, and this can explain the stationarity of blocking. So to get this, we have now, from the blocking identification, we have the location of the block. We put around the box to identify or to calculate the circulation of the block in high. And then we extend this block towards this box towards the south, and the southern edge also towards the east and west to get a trapezoidal shape or a box shape, which is not plotted here. And in each of the fields, I can now identify all the patterns that belong to the vortex individual vortices, but also I will evaluate the total circulation inside the shape. Finally, as a last step, I decide what type of block it is by evaluating the circulations along the latitude of the lows. And if the circulation is higher in these outer 2 boxes, this would be an omega block. If it is higher inside in the middle compared to the other 2 boxes, it will be determined as an high over low. And then we can do statistics and stuff. Just finally, this is an example of one blocking event, and we have again the 500 hectopascal geopotential here in a latitude-longitude grid. And the colors represent the vortex field we extracted earlier. And you see here the trapezoidal shape in solid black, and you see a box shape in dashed lines. So at each time step, I calculate both. So I calculate the box and I calculate the trapezoid, which minimizes the total circulation, as if we have either an high over low block or an omega block. And finally, the method then decides, is it based on this latitude down here where the 2 lows are, if this is an omega or an high over low block. And in this case, it decided it's an omega block, and that's why the trapezoidal shape is solid line. If we now go further, every 6-hour steps, you see that this pattern changes. So the trapezoid is narrowing down, and then the box is the shape that represents this block. So this means it's in high over low in this case. And after a few time steps, we see the blocking low traveling slowly towards the east. And then this shape again changes towards an omega block after a few time steps. And that's very interesting because we assume always that the blocks are quasi-stationary systems, but they are not composed of the same vortices all the time. However, because of this quasi-stationarity, they can produce these extreme weather events which we experience. So to finalize, I proposed a novel blocking classification method, which is based on theory as well as kinematic flow properties. And we already tested this successfully in some papers. The point vortex model has also been proven as a good model to describe these large-scale synoptic weather patterns. And what's really important is to identify the vortices correctly, because this correct identification will give you the correct circulation of the vortex. I will make this method available soon via open source licenses. If you have questions, please contact me. And there's of course still more work to do, and I didn't talk about the stuff and more. So that's for future cases. Thank you so much for your time. I don't know if you have time for questions, and I don't see, don't hear anyone. Can you please tell me if there are questions or if we move on? And to the online people, did you follow it at least? Same. I'm not sure if there are questions online, but please write down. It's my name, LS. So L Schielicke at UVO Canada. If you have any questions, or put them in the chat. Thank you so much. And just otherwise, you can throw me off if you have time constraints. I will have another presentation later, so if you have questions, you can also ask later.
Next speaker.
Okay. Yes. So the next speaker is Daniel Brown from ECCC. And so can I close this?
Where's the presentation?
It was in the folder. Yes, right here, the third one. Yes, exactly. You can use the pointer if you want.
Oh, okay.
Arrows to change slides.
Okay.
Yes, and then if you can speak in the microphone.
Okay. You could also use the handheld.
Use the what?
The handheld microphone.
Oh, I'll just do it.
Cool. All right, have fun.
Okay.
Are we ready?
Yeah. It's good to stay.
So if I press hide here,
You're all good.
Okay.
Okay,
Yes,
good to
we're
go.
ready. Yes.
Okay, can I point this?
Yes.
Oh, it bends, okay. Yeah, so I'm good to start?
Yep.
Okay, I'm Daniel Brown. I work with Environment and Climate Change Canada. And I just want to talk a bit about some work I've done comparing both the GEM model, both the regional and global models with some reanalysis data with observations. And I've focused on severe thunderstorm inflow situations because this arises from being a forecaster and getting frustrated when it was wrong in those situations, especially in those key times. So I just want to thank my co-authors. We were both sort of independently working on this, and we talked about it a few months ago and decided to sort of combine our efforts into this presentation. So, well, that didn't work. Okay, I'll just do it over here. So I'll just talk about low-level winds. So the low-level winds are what I'm focusing on here, and the reason I'm focusing on low-level winds is because that's where I've seen the biggest variability, I guess. And low-level winds are very critical for understanding thunderstorm structure. In particular, they're important for understanding is there going to be a tornado or not from a specific thunderstorm. Many of the indices that are used in forecasting thunderstorms and the type of thunderstorms and what they produce depend on the low-level winds. For example, the storm relative helicity, the low-level bulk wind shear, and all that stuff, those are sort of baseline ones that depend on the low-level winds. And then there are many other thunderstorm indices that are based upon those indices that also sort of indirectly depend on the low-level winds. And so, yeah, once you have significant errors in the low-level winds, that sort of cascades through all the different indices that you use for forecasting thunderstorms. So I'm just going to look at some low-level winds here. So first we have some model versus observation sites. And when I say model, we're talking the ERA 5 reanalysis data in this case. And we compared it from the years there, 1993 to 2021, at the 0Z sounding at a few sites here. So we've got the Paw and Pickle Lake, and Stony Plain is another one. And there's a significant low wind bias in the data in the lowest levels. And that low wind bias seems to disappear as you get higher. So it just kind of suggests there's something going on in the boundary layer. And so we got these charts here. So we got Stony Plain, the Paw and Pickle Lake. And it's basically just a graph of all the measurements that we have. So all the dots are all the measurements and what was observed in the model, in the actual sounding, and what was actually in the reanalysis data. And so in this case, particularly looking at the paw is the worst one, where it's almost double the winds were observed that were in the reanalysis data in the lowest level. And I've only got these two for Stony Plain, but it's similar in all cases. Once you start going into the higher levels, it's all pretty good. The winds are the same, at least on average. You do notice there's a lot of scatter in all of these charts, though. So there are lots of cases where they aren't, but at least on average, there's no specific bias in this case. So the bias is only really in the lowest levels. But it'd be nice if it was just one big, long, straight line of dots, but it's not. So also looked at this at a couple of cases just over time. This is just a couple of different hailstorm cases. And at least the reanalysis data versus the OBS data are quite different, and they're quite different at different times. And it's very hard to see. It's not like one's always half of the other, right? Or it's not like you can just multiply the one by 0.7 and make it work. It's quite a bit of variability, and it's not like it's 10%. It's almost double in places. So I'm just going to go over the low-level wind profile at 4 selected events. It's hard to get wind profile data, as I'm sure most people know. there's sounding sites, which we just looked at. From Edmonton to the PA is a pretty big distance to not have any data. We can do some data with Doppler velocity profiles from the weather radars, and there are some aircraft soundings we can look at. So I managed to find 4 events. I'm sure there's more out there, but it would take a lot more work to find them all. And there was a significant low bias in both the model, so the GEM model winds and the reanalysis winds. And again, this is suggesting there's something in the boundary layer that isn't quite working right. I don't know what it is, but there's something that isn't quite catching the winds as the way it should. So these are photographs. These are 4 photographs, and they're from 4 events, and they're not random events. I picked severe events because this is when this matters, is when we're trying to forecast a severe event. And the thicker black line is the observations, and the other lines are various models and reanalysis. So the blue one is the ERA 5 reanalysis. The red one there's a few red ones. They're different runs of the RDPS model, the regional model, and then sometimes there's a green one, that's the global model. The worst case, I guess I can point out, is that one on the upper right, the Provost hail event. There's a big hailstorm just south of Provost. And so this is from the Schuler radar near Medicine Hat. So that's south of there, but that's where the sort of the low-level jet inflow was coming into the thunderstorm. And so there were no thunderstorms in that low-level jet area where this radar was. It was just clear air. So it's not like there was influence of the wind from thunderstorms. It was just the feeding into the thunderstorm. And you notice how much different the observations are from that radar compared to the actual, sorry, not the actual. So the actual observations from the radar are compared to the profiles from the model and the reanalysis. At first, I was comparing this to the model, and I was going to make this presentation about how the GEM model isn't catching this right. And I was like, well, I'll go look at the reanalysis and it should match the obs. But then it was even worse in the model. So I don't know. It's definitely would prefer that it matched. It'd make things a lot easier. And so I've just got some difference numbers here from the different cases. And again, these are all relatively severe cases. The Provost hail event was, I think, 5-centimeter hail. So pretty big hail. The Calgary was that massive $3 billion hailstorm. And that other one at the top, that was just an EF0 tornado, but it's still a tornado. It still blew down some buildings. So, and I'll just move ahead. I've got a time series. And this is a time series at 500 meters above ground, pulled from whatever I could get. And even over time, the observations are quite different from the reanalysis data. I'll just point out, though, in those bottom 2 at the far end, there's a big thunderstorm outflow boundary, so I wouldn't worry about those differences. That's not predictable from the reanalysis data, but the other stuff is quite a bit different. And then this is the last part. I've got some surface wind analysis for a few events here. Basically, what I did is I took the storm and I drew sort of polygon shape into where I figured the inflow region was, which I did some calculations described up there to figure out where the inflow region was. And then I captured all the weather station data in that sort of polygon shape. Figuring out exactly how to do that was hard. I don't think this is even the best way, but I don't know what the best way is. This is the best I could come up with. And I've just got an example here. The observations from all the weather stations are on the left. In the middle is the reanalysis data, and then on the right is the difference between the two. And you notice how much different the surface wind measurements are going from the observations. This is, of course, this is the worst case that I was able to come up with, but they're quite different. And just got a summary of the events here. Some of them were quite different, some of them weren't different, and that's what makes it hard. You can't just multiply it by 2. There's not much you can do except that, I guess, not look at the model data and look at the observations, but that's hard if you're trying to predict stuff. So I guess, oh, and then I got some time series here showing that it was different for quite a bit of time between the two. So it's really hard when it's wrong half the time, because you don't know when it's going to be wrong. And I was hoping to go through this and try and find a pattern, but I haven't found a pattern yet. Because if there was a pattern, it would make it easier. It seems to be worse in these low-level jet feeding into thunderstorm issues, into thunderstorm situations, sometimes, but not all the time. And the problem with that is that's kind of when we really need to know what it's going to do, because that's when you're sitting there forecasting, when you're trying to make the decision, is it going to be a tornado or not a tornado, is when you need to know that. So having these big discrepancies in the wind and the low levels, of course, like we said before, it feeds into the storm relative helicity, it feeds into the bulk shear, and then it feeds into things like the significant tornado parameter, and they're all affected by it. And like I said, they occur sometimes, not all the time. So you're sitting there trying to forecast stuff. You never know if it's going to be a bad day or a good day for this. I think in the future we need to do a more systematic review of cases, but you have to be careful with that because you end up with this just big smear scatter plot and you can't say much from it. So I'm not exactly sure how to proceed with this, except there needs to be something more cases and a more systematic way of doing it. And yeah, that's all I have to say.
We have time for questions. Is there any questions?
Yeah, Euro 6 comes out next year, I think, or maybe this year. It should be better quality, although I haven't looked at the details. The other thing is that the Euro 5 resolution has probably got a lot to do with the problem. It's 25 kilometers resolution.
Yeah, some of this was in a fairly wide low level. Like if I thought about the resolution, but if it's in a fairly wide low level jet, do you think it would still be in it? But yeah, I'm not sure. Hopefully the 6 stuff is better.
I think it's this year. I thought it was this year, but it could be next year.
Okay.
Another question?
Yeah, you said you weren't really sure why this happening. Do you have any, like, I don't know, speculation why it could be? Or it's like a sibling thing or like some problem physics on themselves?
There's definitely something in the boundary layer. We know that much, I think. What exactly it is, I'm not sure. And the other question is it a regional thing? Because I've looked specifically at Western Canada. Is it happening just there? Is it something to do with the way the air flows on the slope as you're approaching the mountains? That was something I thought of, but I also haven't found a consistent pattern there yet. But maybe it's there if I dig into it deeper.
Yeah, I mean, this is coming from my perspective, plants are this kind of,
Mhm.
you know, atmospheric person, but like, apparently there seems like these dynamics are present.
Mhm.
Yeah, it seems generic. I remember seeing a study recently in southern Ontario where Euro 5 wind speed is significantly different from Connell to.
Okay.
So I don't think it's just a predator.
Okay, that's good to know. Yeah, the concern is that people are. I've been at a number of talks where people will say we're going to use this as ground truth.
Yeah.
And I'm like, it's not ground truth.
No.
So I always get concerned, and I asked someone once a question where I said, why are the observations so different? And they said, well, the observations are probably wrong. And I was like, you have to prove that if the observations are wrong. I mean, it's possible the observations are wrong, but I think the burden of proof is on the observations, not the model, to prove that they're wrong.
And did you look at the HRDPS?
I didn't do a very systematic look at it. I've looked at a couple of cases and it's similar.
It's similar, so 2.5 kilometers doesn't help.
Yeah, it wasn't so much the resolution, it's something else, but I don't know what it is. And like I said, it happens only sometimes, which makes it more frustrating.
Just a final thought, you might want to have a look at ECNWF's website because they do a pretty good job of documenting their models.
Okay.
And procedures, you might find some clues there.
Mm-hmm.
Okay. Well, thank you very much.
Yeah.
So our next speaker is online.
Hello, hello. Can you hear me?
Our next speaker is Connell Miller from the Canadian Severe Storm Laboratory.
Great. Hello. Can you hear me over there? Hello, hello, hello. Hopefully people can hear me. I don't know. I'm trying to talk right now, so if someone in the room could give me a thumbs up if you're able to hear me.
Can
that
you
would
hear
be
us?
We can hear you. Yeah, I can hear you. Hopefully people can hear me. I don't know. I'm trying to talk right now, so
Yes,
if
we can
someone in
hear
the
you.
room could give me a thumbs up. Okay,
If
you're able
great.
to hear me.
Can you
Perfect.
hear
Thank
us?
you. We can hear you. Yeah, I can hear you. Okay, sorry. There's just a huge time delay on
hopefully
here, so
people
I'm
can
just
hear
going to
me.
start
I don't
talking
know.
and giving
Trying
my
to talk right
presentation
now, so-
now. Good morning, everybody. Thank you for taking the time to listen to my presentation today. I'm sorry I couldn't be with you in person. I'm currently out in Alberta helping out with our Hail Field campaign. But my name is Dr. Connell Miller. I'm the director of the Northern Mesonet Project, along with my co-authors, David Sills, Julian Brimelow, and Greg Kopp. I'm here today to talk a bit about the Canadian Severe Storms Laboratory and sort of the history about why we started this initiative and where we're hoping to move forward in the future. So, not surprisingly, severe convective storms are one of the most common and most damaging natural phenomenon in Canada. These storms are the genesis of many thunderstorm hazards, including winds, things like tornadoes, downbursts, and derechos, precipitation, notably hail and flash flooding, as well as lightning. And monetary losses from these storms are on the rise. If you take a look at insurance loss data from CatIQ and the Insurance Bureau of Canada, you notice there's a particularly concerning trend of losses getting larger and larger every year. And again, these are just insured losses. Non-insured losses are probably another order of magnitude higher than this. This is for a few reasons, these increases, according to Munich RE. Number one being population growth. We just have more people that are being affected. Number two being rising property values in exposed regions. It turns out we as humans have the really annoying trait of trying to build expensive houses in coastal areas that are well affected by these phenomenon. And the effects of climate. The effects of climate are fairly well understood for things like flooding and wildfire, but not so well understood for a lot of these severe convective storms like tornadoes and hail. You may also notice that 2024 was a particular banner year for these sort of things. We had the Jasper wildfire that did over $900 million worth of damages. This is actually an image of a suspected fire tornado from that wildfire. We're still doing a bit of analysis to try to figure this one out. The Toronto flooding, almost $1 billion in damages here as well. And we also had, very notably, the Calgary hailstorm. Large section of Calgary impacted. Not necessarily the most severe hailstorm in the world in terms of the size of the hail, but so numerous and in such a large area that it impacted quite a few number of homes. If you take a look at the top 10 natural disaster losses in Canada, you'll see two fairly interesting trends. Number one being that half of them are due to severe convective storms, and 6 out of 10 of them being from the last 3 or 4 years. So again, we're seeing these things on the rise because we're building in these places that tend to be more affected by these severe convective storms. So that's why we formed the Canadian Severe Storms Lab, or CSSL for short, with the vision that the CSSL is the authoritative source for severe convective storms research and data in Canada, thereby improving the safety and well-being of Canadians, with the mission to advance the detection, documentation, and understanding of severe convective storms and their impacts across Canada. So you may be familiar with some of our now what we're calling sub-organizations, those being the Northern Tornadoes Project, the Northern Hail Project, as well as the Northern Mesonet Project. You might notice there's a fourth symbol there. We'll get to that in a second here. But I want to talk a bit about how essentially we got here. Like what is the timeline and how did we end up in this place where a research group at Western University is starting up this severe storms lab? Well, unfortunately, it goes all the way back to 1960s. Where we had Alan Davenport. He was one of the pioneers for wind engineering and wind tunnel testing, where when the World Trade Centers were built, we started realizing that when you start building these really tall, slender structures, that it's not necessarily the weight of the structure that's going to govern the design load. It's going to be the wind acting on it. So they went went to Colorado State University, which was the only existing wind tunnel capable of modeling the atmospheric boundary layer at this time. And then this leads to the construction of the boundary layer wind tunnel at Western University in 1965, which is still one of the defining places to be able to test these structures. And it's tested structures such as the World Trade Centers, the CN Tower, the Confederation Bridge, and the list kind of goes on and on. There's a whole museum in the building that shows you all of these different historical structures being tested for wind. Jumping forward in time quite a bit to 2004, we started realizing that residential homes were being well impacted by these severe winds. So we started what was calling the Three Little Pigs project with, if you huff and a puff, you blow the house down, which is a full-scale testing structure to be able to see how residential structures react in the wind and trying to find the weak links and seeing, well, where can we make these improvements to try to better prevent these storms from happening. And once we started doing that, we realized we needed to actually go out in the field and see where these storms were being impacted. So we started working with Environment Canada at the time in 2006 to do these joint tornado damage surveys so we could start gathering field data that supplements what we were trying to model in the lab here. This also led to the creation of the Windy Dome in 2010, which is our tornado generator over at Western University. And then finally, in 2017, we started the Northern Tornadoes Project with the goal of trying to capture data about every single tornado in Canada. This then expanded to the Northern Hail Project in 2022, where very similarly, we were trying to gather data about every hailstorm in Canada. And finally, in 2024, we launched both the Northern Mesonet Project as well as the umbrella organization being the Canadian Severe Storms Laboratory. So what comes next? So we've made this organization. We've made some pretty big claims of what we're trying to do. Where exactly are we trying to go from here? Sort of three main things that we're currently focused on. One of them being severe convective storms data collection, one of them being research, and one of them being outreach here. So talking about severe convective storms data collection, one of the first things that we did was to start the Northern Mesonet Project. I'm not going to go too much into detail about what exactly this is, but I did give a presentation yesterday about it. So if you missed it, you can always go to your event app and take a look. I promise it's not a terrible presentation, but if you are sick of seeing my face, I get it. It's fine. Won't be offended. But what I will say about it is our goal to connect and enhance Canada's weather network. So we're doing this in two ways, one of them being the Canadian Mesonet portal. So this is a completely free website that we're using to track surface weather stations and data from those surface weather stations with the hope of better nowcasting and better detection of these severe convective storms. The QR code on the screen will bring you straight to the website. So if you're interested in checking that out, you can feel free to do so. We're also putting out our own networks of stations to be able to better detect these storms. So this is our hail station specifically. It consists of an all-in-one weather station, which really isn't all that special. But we do have a hail disdrometer out there that tells us the number of hail impacts we're getting in a region, as well as the size distribution of that hail. Along with that, we do have hopes to start a northern flash flooding project as well. That's that fourth symbol I was showing you earlier. Hopefully to begin within the next 2 years. We're aiming for 2026, I believe, late 2026. Research. So we're really focused right now on tools, techniques, and methods. Number one, to develop multi-hazard damage survey methods. So going beyond like the tornado damage surveys and trying to capture impacts from tornadoes, hail, and flooding all at the same time. Improving intensity estimates, improving methods for detection, and developing climatologies for these hazards. Specifically for improving intensity estimates, we're already making really good progress on that. So for example, this was a project that I worked on to use debris trajectories to estimate tornado wind speeds. It's fairly simple to take an object and say, okay, I know roughly what wind speed it would take to lift this. But when you have something that's, 10,000 kilograms thrown 85 to 95 meters, not necessarily the easiest calculation to do. So we published something on Monthly Weather Review to show the probability of an object lofting with regards to wind speed there. We're also using tree fall patterns to estimate tornado wind speeds. Again, trying to take those patterns and use machine learning to automatically tag the different trees that have fallen in an area to get a sense of what the size and intensity of a tornado going through an area is. And again, we've published that in Artificial Intelligence for the Earth Systems, which is another AMS journal if you're interested in looking at that later. The other facet that I'll mention is all of our data is open access. We're really hoping to just gather all of this data to really empower not only our own researchers, but external researchers to try to do research with this so that we can better understand our climatology. So here, for example, we have our NTP advanced dashboard that gives you tornadoes all the way to 1980. We have the NHP dashboard, which gives you the hail events starting from 2022, but we're hoping to do a very similar advanced catalog in the future, as well as our Northern Mesonet portal, which is giving you live data on surface weather observations and hopefully historical weather observations in the future. And finally, outreach. No research is really worthwhile if you're not reaching out to the public and giving your ideas and trying to change how building codes work in regards to that idea. This was a story that was done for the Canadian Severe Storms Lab in the Globe and Mail. Definitely a bit apocalyptic looking, but I think gets the point across here. And we're trying to improve the societal resilience. So we've worked with building construction companies and we gave them updated guidelines and they're willing to try it. They're willing to say, okay, we're going to use this and we're going to use this as an advertising tool, right? So we're trying to get the public to know exactly what an EF2 tornado is, essentially, right? But trying to also improve building codes. And we're actively working with the National Building Code of Canada and the American Society for Civil Engineers to try to get some of these guidelines that we've shown that for a few $100s, we can stop a roof coming off in an EF2 tornado, which is like 95 to 99% of the tornadoes here in Canada. And we've created documents that have shown this. So we've worked with ICLR to create these foundational documents for high wind safety, which have been implemented as Canadian Safety Standards Association's guidelines here for high wind safety, which is great, but it's not exactly a building code. These are optional guidelines that builders can use to create these high wind safety homes. And we're also doing economics. We want to work with different disciplines, and we've shown that the average benefit to cost ratio for implementing these things is 6-to-1. So not only does it make sense from like a safety perspective, it makes sense from an economic perspective as well. Thank you for your time. Really appreciate it. I'm happy to answer any questions that you might have. Hi, Natalia. Yes, I see your question online there. We would love to get involved with the National Research Council of Canada. If you could just reach out to me at my email, we can get a conversation started and see how we can collaborate in that way.
Very much. We will continue with the next speaker, who is here in person. So the next speaker is Scott Keller from WeatherLogics. Very much. Oh, no. We will continue with the next speaker,
here in Calgary could be billions of dollars. Now, doing a hail climatology is challenging because we don't have a lot of data anymore. One of the most recent climatologies from Etkin in 2018 noted that hail data collection in Canada is now trivial from our public sources. And Brunette and Brimlow, who recently published a hail climatology as we were doing our work, were able to use data from airports or METARs, but that data is more limited. So last year at CMOS, I presented on the WeatherLogic's hail database. I won't go through all of that again in detail, but since 2017, we've been crowdsourcing hail data, and we have over 11,000 reports across Canada. On the map, you can see in blue, non-severe hail, and in red, severe hail. This data comes from many sources, which you can see listed there, everything from social media to phone calls by our staff to affected individuals. So in producing a climatology, we basically started with two key observations. Those being, number one, it seems that hail is very connected to elevation. So we know that in places like the Alberta foothills, there's a lot of hail, and other parts of the world too, like the Alps, Pyrenees, foothills in Colorado, all get a lot of hail. So that was number one. And number two, the observation that the thunderstorm climatology of a given location is essentially an upper bound on what the hail climatology could be if we assume that all hail comes from thunderstorms. So given these observations, we formulated this question: can elevation and the hail thunderstorm ratio be used to produce a reliable hail climatology for Canada? And just to note, by elevation, I'm simply referring to the height above sea level. And the hail thunderstorm ratio is the proportion of thunderstorms at a given location over a period of time that produce hail. For example, if a location gets 10 thunderstorms on average and 5 of them produce hail, that ratio would be 0.5. So how did we go about this? Well, firstly, of course, the data. 3 key data sources for this research. Number 1, the WeatherLogic's hail database. Number 2, a thunderstorm climatology is needed to set that upper bound. That came from the Worldwide Lightning Location Network, which provides a thunder hours climatology globally. And third, elevation data, which came from the USGS. Now, taking the hail reports that I showed you and actually using that for climatological purposes is quite difficult because, as you saw on the map, the hail reports are very, very biased. They're biased towards cities, and they're biased just generally toward population. So you'll see that in the prairies, we do have a lot of reports because we have a relatively higher population density from all the agricultural activity. Of course, southern Ontario and parts of southeastern Quebec also have a lot of reports due to the high population. But because we don't have a lot of reports in the boreal forest doesn't mean there's no hail, it just simply means there's nobody there to see it. So how do we take that data and actually use it? Well, we actually use this bias to our advantage. So what we did is took just simply urban areas and calculated the hail climatologies just for those urban areas, and then developed the methodology then to translate that climatology everywhere else. So the question was, well, which urban areas were well enough sampled to actually produce a climatology? In order to do that, we created this plot. This chart is showing what's the relationship between elevation and the hail thunderstorm ratio based on the number of reports in a given urban area, or you could think of it as a given city. So if we have 0 report, so any city that has 0 reports or more has a very weak relationship. R squared is very close to 0. But as the number of reports in a given city increases, it's better sampled and the relationship gets better to a point where it levels off. So for all hail in blue, it levels off at about 41 reports. And for severe hail, greater than 28 reports, you get a stable relationship between these two factors. So the result, well, if we then create linear regression models using that data, we can do that for both all hail, which we define as having a diameter of greater than 5 millimeters, or about pea size, or for severe hail, which has a diameter of greater than 20 millimeters. Each dot on the regression plot is one city, and it shows the linear relationship between elevation and the hail thunderstorm ratio. And it turns out those relationships are actually quite good. So for all hail, R squared is 0.78, the correlation being even higher, which I'll show later. And for severe hail, the relationship is also relatively good, but it's lower, it's at 0.65. Now that we've got these relationships, we can actually calculate the hail thunderstorm ratio anywhere in the country. All we need is to plug in elevation, and for every point where we have elevation data, we now know what the hail thunderstorm ratio is. So you can see on these plots, for all hail, the hail thunderstorm ratio is highest, obviously in areas of higher elevation. So that is in parts of Alberta, along the foothills into the Rockies, BC, and even in parts of the north. Now in the eastern half of the country, those ratios are lower, but we still get hail, so I'll show how we account for that in a moment. For the severe hail thunderstorm ratio, the pattern is very much the same. The key difference just being that the ratios are lower, so the proportion of storms that produce severe hail is just less. And here I've also noted the correlation. So for all hail, the correlation between elevation and the hail thunderstorm ratio 0.88, and for severe hail 0.81. So the result, we now have our hail climatology when we just multiply those maps of ratios by the thunderstorm climatology. So multiplying the hail thunderstorm ratio at any grid point by the number of annual thunder hours gives us the number of annual hail hours. So this map shows a lot of the patterns that you would expect. So in the Alberta foothills, we have a maximum nationally in hail with 6 to 7 days per year. And then in other parts of the country where you would expect hail, like the southern prairies, we have another local maxima. Even in the BC interior, a lot of past climatologies have shown a lot of hail in the BC interior, even though people maybe don't think of that as being a hail-prone area. But the higher elevation plays a big role there. In eastern Canada, we also do get hail, but not nearly as often. But we do see a local maximum in southern Ontario. And that's in large part due to the fact that that area simply just gets a lot of thunderstorms. So even though the ratio or proportion of storms that produce hail is relatively lower, the number of thunderstorms just increases that to create that local maxima. And in looking at these maps, you'll note that they're all in hail hours, which is a bit unusual for a climatology. Normally you would look at it in terms of hail days. The reason it's all in hours is because that was the thunderstorm climatology that was available to us. But fortunately, hail hours and hail days are nearly identical. So we did do a further analysis to quantify that relationship, and actually the correlation between hail hours and days is 0.98. Just a note that when I talk about hail hours or days, these are not durations. These are just simply 1 hour that had hail is considered a hail hour. It doesn't actually have to have lasted for a full hour. For severe hail, the pattern, again, is quite similar. The numbers are just smaller. So we see in Alberta, along the foothills, we have, again, our maxima with up to 2 days with severe hail per year. And even in places like southern Ontario, we have a local maxima in the southwestern part of the province. One thing I didn't note is that all of the grid cells on these maps are 10 kilometers by 10 kilometers. So everything was normalized to that area, including the data from the urban areas that we originally used. We normalized it down to 100 square kilometers. So in discussion, we thought a lot about kind of what this told us, because I think the maps that you're seeing probably won't come as a big surprise. They kind of mimic the patterns we would expect to see in a hail climatology. But firstly, we wanted to see, do our results match with other work? Now, the challenge in doing that is the fact that when you're dealing with hail, these storms are so small in scale, you need to really be certain that you're comparing one-to-one. So if you're comparing your hail thunderstorm ratios or your hail climatologies to others, they're conducted on the same spatial scale. Now, in comparing our hail thunderstorm ratios to other works that have been done, we really were unable to find any that use the same spatial scale. But just in general, if you look at other studies, let's say in the United States, they find very high hail thunderstorm ratios in the Rockies of Montana or around Denver, and they find the lowest values in places like Washington, D.C., where they're nearly at sea level. And secondly, another very important point, when we're talking about these types of linear relationships, we're not concluding that elevation is the reason for the variability in the hail thunderstorm ratio. We speculate that just generally it's a very good proxy for this relationship. But what could be the physical factors behind it? This is not something we studied, but we're speculating that freezing level probably plays an important role. At higher elevation, the freezing level is lower to the ground. And also storm mode could be an important explanation, particularly why this relationship starts to break down as hail size gets larger. So in conclusion, The model explains a majority of the variability of the hail thunderstorm ratio, at 78% for all hail. And the reason why I really like to emphasize that is because we hope future studies will build off of this, and they'll actually have a quantitative measure to use to compare their climatology to. Secondly, I already alluded to this, but the relationship seems to break down a bit as the hail size gets larger, and we speculate that's because storm mode plays a more important role. We know in places like Southern Ontario, they don't get necessarily a lot of hail days or hail hours, but they do get notable severe hail events, and that could be simply because they don't necessarily get a lot of the small hail, but when they do get a hailstorm, maybe it comes from the fact that they get more supercells. And in terms of future research, we encourage people to try this relationship in other parts of the world. I noted yesterday in a talk, someone who was researching hail in Bangladesh noted that hail there also tends to happen at higher elevation. And then secondly, what are the true physical causes of these relationships? Could it be freezing level, or could there be other factors at play? Well, that's all I have, but if you have any questions, feel free.
Very nice thought. Curious, the insurance industry uses flood risk maps to underwrite flood insurance. Do you know if the insurance industry is using something like this to underwrite hail insurance, or is the insurance industry working with you on this?
Yeah, we have done some insurance projects using this data already. So they're very interested in using it. Surprisingly, right now, they're using pretty rudimentary methods to figure this out, generally just based on their past claims history, which often isn't good, especially if it's a new neighborhood where there's no past claims history. But we're already starting to use this for the insurance industry, and I think having this more precise data that's going to be verified and peer reviewed will be a big benefit to them.
Another question?
I think yesterday there was somebody from Canada that showed the differences between the West Coast and East Coast in terms of the above ground, the polarity of the lightning strikes. Do you think there's some correlation of the duration?
Yeah, I really couldn't comment too much on that. I haven't studied the relationship between the polarity. The data that we used in the study was just total lightning, so we didn't get into those details.
Okay, thank you.
Could you say something? Okay, yeah. Thank you so much. I can start, right? Sorry, can I start now?
Did you say something?
Okay, yeah. Thank you so much. I can start, right? Okay, I will just go along. Thank you so much for having me again. I would like to show insights from a university modeling shop where we used Cloud Model 1 to explore cloud dynamics. And I think this fits very well into this session as well. It's educational, but on the other hand, students use their theoretical knowledge to analyze or to apply this to a model and analyze what they've seen. And you see here in the background, one of the figure or this contribution in general, this presentation was done with 4 of my students and another colleague. And the picture in the background is derived from this workshop, was in one of the research projects of one of the students, where we can see a supercell thunderstorm, which forms a tornado-like vortex, which is enwrapped in rain. So why should we teach convection resolving modeling in the university? Well, on the one hand, students usually are fascinated by thunderstorms and clouds, at least students in atmospheric science, meteorology, climatology, and atmospheric physics. However, in German, so this is from a German university course, and in Germany, usually these topics are not covered in that detail in the curriculum. However, it's important because most of our students go into numerical weather data analysis or to weather services, where they then form or shape the future models and either weather models or climate models. So the goal for this course, specifically for this block course, was to understand moist convection, develop practical skills, and foster research ability. Here I give a short overview over our 2-week course, so 10 days in total. To run the model, we had the ability, or we were able to go to a high-performance computing cluster at the University of Bonn. So the students learned the basics of this high HPC computing. We introduced Cloud Model 1 on the first day. On the second day, the students already produced their own first simulation of a supercell thunderstorm. And then they also got training in 3D visualizations. However, you will see, I didn't give the training. There's a lot of material and they worked through it. And over the rest of the week, we also used all the abilities which we can use with CM1. So we used how to simulate a simulation using the name list. We changed the code. We used external soundings, and we also digged into terrain. And finally, in the second week, the students chose their own project and then had to finish with a report in the back. And the target audience at first was atmospheric science students or meteorology students with a basic background in dynamics or modeling. Cloud Model 1 is, I would say, a standard model in the United States to investigate idealized or to analyze, to simulate idealized convective storms. I copied this here from George Bryan, the developer, from his website. In non-scientific terms, CM1 is a computer program used for atmospheric research. It is designed for studies of relatively small-scale processes in the Earth's atmosphere, such as thunderstorms. Why is it a good way to choose CM1 for educational use? So on the one hand, it's written in Fortran, as are all the other models we use in climate and weather science. It is open source, and it allows you to change the source code, which we also used. And there are many pre-configured cases and many publications, and it allows for idealized studies to better understand what happens, what the processes are in convective storms. So like I said, on the first day, we had just a small practical training with over the whole time, in fact, about high-performance computing clusters. So the students learned how to use Slurm, how to work on an HPC cluster, which really enables them for their future career to use these HPC systems. And they understood how an HPC cluster worked. The 3D visualization of the cloud dynamics was done in my case, I choose to use ParaView, but one student already know another 3D visualization software, Vapor, and he used this. And I chose ParaView because it's open source, a 3D open source visualization program, and it has an extensive online learning resources. So the students work through the online resource, and then after that, during their project, they produce 3-dimensional visualizations of their data. For example, here one of my students, Yidan, she studied shallow cumulus convection over the ocean, and she tested here different parameter or different mixing ratios at one time steps, and also played around with lightning. Another student project, Pablo, he studied high and low precipitation supercells compared to the original Weissman-Clemp supercell in Italy, so also over terrain. And here on the right, for example, you see two different mixing ratios of graupel for the high precipitation supercell and for the low precipitation supercell. On the left, for example, is the reflectivity for these two cases, high precipitation supercell, low precipitation supercell. Jerome studied different triggers and modified soundings to initiate the Moore tornado outbreak, or the Moore tornado of May 3rd, 1999. And like Daniel's presentation, we also used ERA 5 soundings, vertical profiles to initiate this storm, and the original profile failed because it was too dry. And I think in our case, the wind profile was fine, but we observed that it was too, so the boundary layer was also not completely correct. So Jerome took the sounding and modified the low-level mixing ratio, for example, and also the potential temperature profile. And then he tested different trigger mechanisms to observe how this affects the convective appearance or the storm type. For example, here in this case, we have the reflectivity patterns in an horizontal way, and you see here is more separated single cells, while the right-hand side with the different sounding gives more a whole squall line. And Aaron tested convection in weakly sheared situations over real terrain. And in the example you see here on the right-hand side, he produced a cold pool and investigated the vertical vorticity that forms at the edges of the cold pool, which can also lead to some damages. I asked my students, so in the first time I did this block course, I just had 4 students, and I asked them to self-assess what they know before the course and after the course. So I asked them how good they know about CM1, HPCs, DERM, CDOs, visualization techniques, etc. And their answers there before the course are all given in blue. So most of them are on the, I have no knowledge or little knowledge or maybe moderate. And after the course, the answers are given in orange. And you see that so we see a main shift from them in all of those topics I asked for. And even so, CM1 is now a very specific model. It also helped my students to improve in topics that are not directly related just to this model, but will be related to other models, which gives them better career chances, to expect. I also asked them what did they like. So one student said, for example, the course included everything important. We had enough time for our own simulations and various experiments with different soundings. Questions were addressed in detail and help was always available when needed. I also asked them what we can improve. So some of them wanted additional topics. So for example, including trajectory modeling, which is possible with CM1. And also to compare the model with other modeling systems, like other weather models, for example, and allow more time for practice. So some students asked for having a 3-week block course instead of a 2-week block course. My takeaways from this course is that, on the one hand, CM1 is a great model to introduce you into the realm of numerical weather and climate models, and you can relatively fastly get your first simulation running and can get hands-on learning of moist convection. The HPC part of this block course gives you real-world modeling skills, and visualization is always the tool you need to visualize your data. And this visualization can also help you to understand better cloud dynamics. And the students gain quickly confidence through guided practice here in my course. The course led to, I did the course the year after again, and now at the moment I'm adapting the course material to Western University, and overall, the course led to several student thesis and research projects and 4 bachelor theses, 2 master theses, and 2 summer students at the moment who are also working at the CSSL, or also co-working in the CSSL summer internships, or cooperate with the summer internships of the CSSL. And I think it's a great way for, especially for senior students, but the students I have now are undergraduate students. One is from first year and the other from second year, and both are from physics or from science. One of the bachelor students was also third year physics student. And so that's why I adapted the learning material also for these students. So finally, I would like to advertise it a bit. So the course material is published on a CC BY 4.0 license. You can find it here on ResearchGate, and the paper together with the students, where all the pictures or all the figures came from in this talk, can be found here. And I would like to conclude this talk with the visualization of a student, and I think this of here Jerome, whose figure I also took for the beginning. We see here the splitting supercell, Weismann-Clem supercell idealized case with the right moving supercell here in the middle, and he used his theoretical knowledge he had from books to now annotate the structures he sees. So the gray part is the cloud structure, so everything mixing ratio for rain, droplet, cloud particles and snow particles and so ice particles. These are all forming the cloud structure here. We can see the overshooting top, and then on the ground you have the reflectivity pattern, and in this inset is also a horizontal picture of the reflectivity pattern showing the hook echo he marked down here. Thank you very much. I probably need to answer questions in the chat, and I'm happy to do that. Thank you. Sorry. I see a question. This is about you focus on cloud dynamics. Is there anything about cloud microphysics in this course? Not specifically. I had an extra course at the university about microphysics, and I had a bachelor thesis who someone investigated different microphysics schemes and how they affect the dynamic of a score line. It's up to the students. So when they do their extra project, they can decide on testing different parts of the simulation. So microphysics is a part of the name list, for example, to change the name list, but we didn't change microphysics ourselves. But it's definitely possible, and it's relatively easy to change between different microphysics schemes and then investigate or do your research according to this question, how microphysics might affect a supercell, or some other convective cloud system or other cloud systems. someone asked about the resolution of CM1. You can do the resolution down to a few meters. So the last simulation done by Lee Orff's group was, I think, around 30 meters. My students used I think the minimum was 250 meters, because otherwise you get so much data and this blows up your HPC cluster. And but it's possible to, so the pre-configured case of the supercell, for example, is 1 kilometer in resolution, and then we usually changed it down to maybe about 500 meters or 250 meters to see more of the structure of the storm, like the hook echo, for example. And also for the time resolution, you can, the output or the simulation runs with a few seconds. So, and then you can choose to give the output every few seconds, or we usually aim for 5 minutes. That gives a smooth visualization of the structures. But this really depends on the thing you are looking at. For example, this shallow cloud simulation one student did, there the output is maybe 30 seconds to see the evolution more clearly of the shallow cumulus clouds. I think the 30-meter run needs a lot of time, and you need a lot of resources. It's a parallelized model, so you need a lot of nodes. So I have to look in the paper. I don't know how long if they give more information, but if you want to, I can add the YouTube channel of Lee Orff there. He also sometimes presents these results.
Thank you to all the speakers for this morning. And I invite you to participate to the job fair at lunchtime if you are interested. And I think this is the last session now on this topic too for the conference. So thank you all.